Section 7.6, we're looking at connected particles, and very similar to section 7.5, we've seen everything here before. We're just applying it to probably the sort of pinnacle of how fiddly these questions can get. We have, in most of these questions, we've got an object on a plane, which is an inclined plane. It's not a horizontal table. It's also going to have a rough plane in most of the questions, so it's not a smooth inclined plane, it's a rough horizontal plane, so we've got to take account of friction. Then it's not just an object on its own, it has, in most of these questions, a string attached to a pulley, which is then attached to a separate object down here. So at AS Maths, we had a lot of things that look like this. Now we're going to have a lot of things that look like this. In the same way as hopefully you cracked the AS material, eventually we got used to these. Well, we're going to get used to these things in exactly the same way. What did we do here? Well, we cover this bit up and we look at the forces acting on this this part of the system. Then we cover this bit up and we look at the forces acting on this part of the system. Well, we're going to do exactly the same. We'll cover this up and look at the forces here. Well, that's the same as last year. Look, if I put my hand over here, these two diagrams look pretty much the same. If I cover this bit up, then we're going to look at the forces acting on this bit. Well, that's going to look very like the questions from earlier on in chapter 7, isn't it? So yes, they're going to be fiddly. Yes, they might be moving and accelerating even this time. But that's all things that we can deal with if we break it down into small enough steps. The other thing that could well happen is all the things that were nasty last time, where this thing gets moving, the whole system gets moving in one direction or the other, and then somebody cuts the string. And what happens? How does this thing fall to the ground? Or the other thing, yeah, this thing hits the ground, and then this thing slides along the table. This thing hits the ground, and this thing slides up the slope, and then starts sliding back down the slope. In other words, we start off with one of these questions, and halfway through it becomes a SUVAC question. But again, we have all the information we need to cope with that. So there's the general gist of it. All I can really do now is go through the examples, and hopefully that will get you there. So, example 11. We've got two particles, P and Q, of masses 5 and 10. Page 150, if you're following this through. We've got a mass 5. Actually, you know what? We're going to need a bigger diagram than that, so let's extend it. Here we go. We've got a 5 kilogram mass here. So it has a 5G force acting down. There's a reaction from the plane. They're connected by a light inextensible string, and the string passes over a small smooth pulley which is fixed at the top. So here's my pulley, here's the string. This one is P, this one is Q. This one has a mass of 10, so it's got a 10G force pushing down, and there's a tension in the string there, a tension in the string there. At the moment, I don't know whether this system is moving or is stationary. If it's moving and accelerating, then I'm going to be using some F equals ma. If it's stationary, then I'm going to be balancing forces out because we're in equilibrium. Let's keep reading. Fix the top. Now, this is a rough inclined plane, so there's friction, but at the moment I don't know whether this is moving upwards or downwards or anything like that, so I can't put the friction in yet. Let's hold our breath and find out which way it's going to go. P rests on the inclined plane and Q hangs over the edge, so I've got P here and Q here. Which actually, I didn't know which way around they were until that part of the sentence, but I cheated because they've already got a diagram for me in the book and I just copied which way around they go. P hangs on the edge of the plane with the string vertical and taut, so there is a tension in the string. The plane is inclined to the horizontal at an angle of alpha, where, surprise, surprise, tan alpha is 3/4, as it so often is. So let's just, let's do it this way around this time. We've seen this a lot of times before now. If tan of alpha is 3/4, we can imagine there's our alpha. Opposite over adjacent is 3/4. So sine alpha is 3/5. Cos alpha is 4/5. And we'll save that information. The coefficient of friction between P and the plane is 0.2. Now, I've got to, the system is released from rest. I've got to the end of the information. So it doesn't really matter what they're going to ask me next, okay? There is one extra little bit of information, which is find the acceleration of the system. So if they're asking us to find their acceleration, there must be an acceleration. And in this case, if this is a smooth pulley, this is a 10G weight, it's going to be moving this way, isn't it? Because this a 10 kilogram weight, this is a 5 kilogram mass here. So this one's pulling down more than this one. So I'm going to go for the acceleration positive, I think, will take us that direction. The acceleration is going in the direction I've just labelled as positive. That means the friction is going this way. It is moving, so that friction is maximum, which is mu times r. So how do we do this? We say at Q, we'll look at the vertical forces, 10g goes downwards, t going upwards. We know it's accelerating downwards, so 10g minus t equals mass, which is 10, times acceleration, which is a. So at Q, vertically, apply F equals ma. Can I just stress the point, which perhaps I haven't done enough already? This bit here is absolutely vital. Don't just write this equation down without explaining where it is. In the two reasons, as always. One, it's going to keep your thinking clear, which is going to mean that you're going to get the answers right. And two, in the mark scheme, it will often say for trying to apply F equals ma at Q. Well, in that case, if you've written this, they know that that's what you're trying to do. So even if you get this equation wrong, there might be marks for it. And then the third reason is it makes it easy for the examiner to allocate the marks because your answer is going to be right, and therefore they want to give you the marks. But if your working out is really muddy, they might miss marks that you deserve to get. So make sure this sentence is there. At P, we can do two things. We can go parallel to the plane and perpendicular. So let's go parallel to the plane. We know this is accelerating in this direction, and that's the direction we're calling positive as well. So we're going to apply F equals ma. That means that tension pulling up the plane, this angle here is alpha, minus mu r, which pulls down the plane. Ignore r because it doesn't go up or down the plane, and then the down the plane component of this 5g. That's my resultant force. That equals mass. Mass, which is 5, times acceleration, which is a. We can go perpendicular to the plane. Perpendicular to the plane here on P, there is no acceleration. So the out of the plane forces, that's just r, equal the into the plane forces, which is the into the plane component of this 5g force here, which is 5g cos alpha. So resolving forces in that direction gives us this. We have equation number 1, equation number 2, equation number 3. Is there anything else that we need? Well, now it's worth us looking back. Can we find the acceleration and the tension? Here, the acceleration and the tension are linked in the equation, but we know everything else. Here, the acceleration, we need r, but then we'd have a second equation with acceleration and tension in. And that's fine because if we take r from equation number 3, we can put it in here. So these three equations, when we look through them, the things that we don't know are a, t, and r. I've got 3 unknowns and 3 equations, so we can do the job. You might be looking at it thinking, well, what about this alpha? Well, look, I know sine alpha, and I know cos alpha, and I know tan alpha. So I can, I know that bit, I know that bit, I know what 5g is, I know what mu is because it tells me up here. So the only things that are missing are t, a, and r. And between those 3 equations, I should be able to work those out. If I'm really being clever, then I can work out that I take equation 3 and substitute into equation 2, and then I take equation 1 and equation 2 and solve those simultaneously. So that's the point where the mechanics is over. Okay, we're into just simultaneous equations, and I'm going to let you follow that one through with the blue box on page 150. As I keep saying on this chapter, I may as well do example 12 because it's there if you want to see it. If you don't want to see it, then there's no need to keep watching, is there? So, on the end of a light and extensible string, we have attached to a block A, which has a mass of 2 kilograms. The block A is held at rest on a smooth fixed plane, which is inclined to the horizontal at an angle of 30 degrees. So, block A is on a smooth fixed plane. It's got a mass of 2 kilograms, so it has a weight of 2 times gravity. There is a reaction force there. This plane is at 30 degrees to the horizontal, therefore this angle here is 30 degrees as well. The string lies along the line of greatest slope of the plane and passes over a smooth, light pulley which is fixed at the top of the plane. In other words, different words, but our usual arrangement so far. The other end of the string is attached to a block of mass 5 kilograms. 5g pulling down, therefore there's going to be a tension in this string. The system is released from rest by modelling the blocks as particles and ignoring air resistance. Show the acceleration is this, show the tension is this. Now, in this case, this plane, it says, is smooth. Okay, so if this plane is smooth, there's no friction involved in the question. So I already have all the forces that I need, but it does tell us that we've got an acceleration going on. So that's that way. That acceleration is this way for this part of the system. And what else? Let's make positive that direction here, I suppose. And I suppose over here, positive is the downwards direction. So this we're calling A, this we're calling B. Now hopefully you'll be able to see the pattern here. I'll start at B because I started at this bit last time. We're going to go vertically and we're going to apply F equals ma. That means that 5g minus t, that's 5g pulling down, t pulling up. So that's my overall force, equals mass times acceleration. Oh, but mass I know is 5. At A, going parallel to the plane first of all, I have some acceleration. The upwards forces are t, the downwards force is 2g, oops, t, take away 2g sine 30 degrees. That is equal to mass, which is 2, times acceleration, which is A. Still at A, going perpendicular to the plane, we are resolving forces, balancing them out because the forces pushing out equal the forces pushing in. So R equals 2g cos 30 degrees. 2g pushing out, R pushing out, 2g cos 30 pushing in. The tension doesn't do anything in that direction. So there we go. There's equation 1. There's equation 2. There's equation 3. Now we go back. Show that the acceleration is this. Show that find the tension in the string. So can I do that from these equations? Hopefully I can, because what have we got that we don't know? T and A I don't know, T and A I don't know, and R I don't know, but actually I do know R, don't I? It's just 2g cos 30. I don't even need this third equation in this example, it turns out, because these two equations are two equations with two unknowns. So this one happens to be redundant for the moment. That's fine. I don't mind having the odd redundant equation. I'm still sticking to the same pattern. Those are the three things that I can write down, and then I'll work from there. Now find the tension in the string, find the acceleration. Okay. Now then, part B is a modelling assumptions question. So how have we used the fact that this string is inextensible? Perhaps that's familiar to you from the AS level stuff, which is if this string stretches, well, when I release this from rest, maybe what happens is A stays here and B just sort of goes down, moves a bit, bounces up and down on this string in some way. If this string doesn't stretch, so imagine it being an extremely stretchy string. This is like an elastic band. Then you can imagine there being some pull in it, some bounce. So that would mean the tension is not the same throughout the string. Okay, so that's one of our sort of core assumptions. That's one of the things we know. That's what we mean by inextensible. Now calculate the magnitude of the force exerted on the pulley by the string. So this is slightly out of the run of what we've been doing, but this is the other question they can then tack on to the end. It doesn't make our whole process any more complicated, because what we do now is we realise that actually this tension's all the same all the way through the string. So if we just focus in on the pulley, if we cover everything else up, if we cover all that up, then we've just got this, okay? Now let's just draw that part of the system out down here. I've got two forces acting on the pulley. It's tension and tension from the string pulling down, tension from the string pulling down there. And we've just found in the earlier part of the question, when we solved these equations here, that the tension is 15 over 7g. 15 over 7g. So we've got two forces there, and I want to know the resultant force. What is the force that's pulling on this pulley? Now actually, this pulley isn't accelerating in this direction, is it? So the pulley has a reaction force, which is going to be equal to the resultant of these two forces. Sometimes they phrase the question that way, find the reaction force at the pulley, which is going to be equal to the resultant of these two. So what is the resultant force from these two? Well, we can work that out because we know the angles that we need to know that this is here is 30 degrees, and then I can work out the vertical component of both forces, which is 15/7g from this one and 15/7g sine 30 from this one, and then I can work out the horizontal component, and then I've got I can think of it as vertically and horizontally. I know what those things are, so I can work out by Pythagoras theorem the magnitude of the resultant. Okay, so we can do it that way. And just to finish that off, horizontally, the horizontal component of this force is 15/7g cos 30. Okay, so that is 15/7g plus 15/7g sine 30 pulling downwards. Pulling to the left is 15/7g cos 30 degrees. And then if you work that number out, and you apply Pythagoras theorem, that tells you the magnitude of this force. And you could also, if you wanted, work out the angle to the vertical or the angle to the horizontal at which that force is pulling. I just noticed that in the book they've done it a different way. I'll just pause and have a look at what they've done in the book, see if it's any different. And so in the book, the third part of this question, they've done it this way, which is quite neat. I think I would still stick to the way that I've done it, but in case you're interested, again, no need to watch this video if you're not really. You can just stick to my method. We're going to think about it like this. Here is a 30-degree angle. There's 90 degrees. So this here is a 60-degree angle. There is tension here and there's a tension here, and they're both the same size. So the reaction force is going to cut this angle here in half, isn't it? So that's going to give us 30 degrees here and 30 degrees here. So if I just draw those three forces out, there's a tension there, there's a tension there, there's 30 degrees there and 30 degrees there. So what's the total from these ones, from these two forces? And I can think of it like this. So there is a right angle, okay? So what component of this force here acts in this direction? Well, if this is the tension, then tension times cosine of 30, right? So this force here is, let's cover this bit up. Oh dear, you can't see for the shadow, can you? So that tension there acting in this direction is T cos 30 degrees from this one. And then from this tension force here, we have another one of those. So there's another T cos 30 degrees. So two lots of T cos 30 degrees. And then T, it turns out, is 15/7g. So there's another way at the answer. Personally, I find that a bit fiddly. I think my way is more intuitive, but then that's why there are different methods. Obviously, other people find that more intuitive and would find my way of doing it a bit fiddly. Up to you, I guess. Right, a very long video, I know, but there is a lot to discuss there, and hopefully you have found the bits that were useful to you and used them. Now, there we are. That is definitely, I think, without question, the hardest mechanics chapter, and we are at the end of it. Good luck with the practice. You will need a lot of it, a lot of practice, that is. But hopefully, if you just apply those same rules, apply the equations you can, solve them all simultaneously, then eventually you'll get there. End of chapter 7.